All right, today for geometry, we're doing 5-4, which is indirect proofs. Our objectives today, we're going to state the steps in an indirect proof. Okay, we're going to find out the steps. We're going to identify contradictory statements, and we're going to complete some indirect proofs of algebraic and geometric statements. So a lot of new vocabulary, kind of an ideas today. So first of all, direct proofs. Direct proofs are what we have when we start with given information and we follow the implication. So the definitions, the postulates, the theorems, all that stuff that led us to the conclusion. This is what we have been doing all year this year. Whether it was a 2-column or a paragraph or a flowchart proof, they were all direct. We had given information, we used the definitions, postulates, and theorems to draw a conclusion. We're moving into this idea of indirect proofs today. Okay, so indirect proofs. We're going to temporarily assume the conclusion is false. Okay, so what they're telling us is the conclusion is wrong. Then we're going to show that this assumption, so that falseness, leads to a contradiction. Okay, when we have that contradiction, if it contradicts that, then this implies that the original statement must be true. So it's kind of bizarre, okay, for this indirect proof. We're going to assume the conclusion is false. We're going to show that that's actually a contradiction, and therefore the original statement is true. So in most indirect proofs, the statement and its negation are the only possibilities. Okay, so it's going to be like, Miss Talbert's shirt is red, or Miss Talbert's shirt is not red. Like it's one or the other when we're looking at these indirect proofs. Miss Talbert is wearing jeans today, or Miss Talbert is not wearing jeans today. It's one or the other. Like I either am or I'm not. Okay, so that's going to help us a little bit with indirect proofs. Remember back to conditional statements. Okay, we have this conditional statement. So if P, then Q, all right, is logically equivalent, so it's equivalent to the contrapositive, that not Q, therefore not P. Or if not Q, then not P, I should say. All right, and also crammed in there, it's also called a proof by contradiction. Okay, so those are all things about this indirect proof that we're going to look at today. So first of all, we're not going to dive right into that indirect proof. We're going to look at some examples to help us out. So for each conditional, state A, the contrapositive, B, the truth value of the conditional, and C, the truth value of the contrapositive. All right, so the first one I've done all the parts of. So our conditional, first of all, if a triangle is isosceles, then, right, there's the then, so that's our arrow, its base angles are equal. So we've got if P, then Q. Okay, so if we want to state the contrapositive, okay, the contrapositive, remember, is not Q, then not P. So we have if the base angles of a triangle are not equal, then, so that's our not Q, it's not isosceles. Here's our not P. So there's our contrapositive. Now we want to state the truth value. Okay, so of our conditional, if a triangle is isosceles, then its base angles are equal. Remember when we talked about an isosceles, so this side and this side are equal, these are their base angles. Yes, their base angles are true, or are congruent, so that's true, or equal. So then the contrapositive, if the base angles of a triangle are not equal, so if we have this triangle, and this is side 1, side 2, and side 3, we'll say, there's no, oh sorry, side 2, the marks keep stacking on top of each other, then there's no way that these two angles are congruent. So that's true. Okay, let's look at 2. if a natural number is prime, so natural number is prime, then it's an odd number. Let's write the contrapositive. So if a natural number, so we're keeping that. So maybe let me go back up here and erase the natural number part. We've got prime. Okay, so the natural number is not odd, then it's not prime. So we flip those orders. Okay, so let's look at the truth value together. If a natural number is not an odd number, then it is not prime. Well, I know that 2 is a prime number, but it's even and not odd, so that makes this false. And it makes this one false, because the other thing you know is they are equal. The conditional and its contrapositive are equal. All right, so let's do this last one together. If a conditional is true, okay, so we have true, then its contrapositive is true. Oh, I don't know why I put that arrow there. Pardon that. Okay, so let's see if we can write this. If a conditional is true, then its contrapositive is true. Okay, so I'm going to write conditional. All right, so we want to flip these. And instead of saying not true, right, we could say not true. We could also say false. So let's do that. So if, we're going to change this to if a conditional's contrapositive is false, right? Not true. So it's false. Then the conditional is false. So if a conditional is true, then its contrapositive is true. Well, we just talked about how the conditional and the contrapositive are equal, so this has to be true. So if a conditional's contrapositive, or we could just say if a contrapositive is false, then the conditional is false. Well, that would also have to be true because they're equal. We talked about earlier. The conditional and its contrapositive are equal. So both of those are true. All right. So there's our first start, like looking at some of these contrapositive things. All right, so our first objective was writing the steps in an indirect proof, and here they are. All right, step 1, okay? You're going to assume the opposite or the negation of the conclusion. Okay, we're negating the conclusion. 2, you use the assumption to reason deductively, okay, but you're reasoning to a contradiction of the given information, your assumption, or a known fact. So you can use definitions, postulates, or theorems. And 3, step 3, we're going to conclude that the assumption must be false, and that the statement, therefore, that you are trying to prove is true. So the statement you are trying to prove is true. Probably sounds weird, and I get that. It's going to make a little bit more sense when we actually do some. Okay, so first of all, this law of contradiction theorem, though. Let's look at that. So if an assumption leads to a contradiction, then the assumption is false and its negation is true. That's what we're going for. Okay, earlier too, I said that In indirect proofs, we're going to be using these statements that are like they either are or they are not. So this one, right, this is an example. The measure of angle A equals 90 degrees. The negation of that, or the opposite, is angle A is not a right angle. Okay, so it doesn't, the measure of angle A does not equal 90 degrees. It either does or it doesn't. Contradictions, both cannot be true at the same time. Only one can be true. So if you find yourself writing one, you're like, well, wait, both of these can be true, then you haven't actually written the contradiction. Okay, all right. Let's look at example 2, where we're actually going to write a proof. Okay, so these are just, again, this is our first time seeing this indirect proof. We're going to look at a couple examples first, and then we'll do one. So example 2 first. Okay, write an indirect proof showing that if x equals 4, then 3x plus 7 does not equal 22. Okay, so this right here, right, we don't see not equal a whole lot. So that's new. So in our proof, we've got step 1 here. We are assuming we want to negate this conclusion. We're going to assume then that 3x plus 7 does equal 22. We assume the negation of the conclusion. And then we're going to solve it. Okay, so we subtract 7 and we get 3x equals 15. Then we divide by 3 and we get x equals 5. Okay, so right there we just did the addition property of equality, the multiplication property of equality. And now, so that was all that step 2 work. Okay, so that was all step 2 there. Which if you go back and look above, step 2, right, it says use the assumption to reason to a contradiction. So we reason to a contradiction that's kind of, you know, it's on the same level of x equals 4. We got x equals 5, but it's a contradiction. So now we're ready for that step 3. Step 3 was you're going to conclude that the assumption must be false and that the statement you're trying to prove is true. So here, step 3, we have, but, I love that, but x equals 4. That's what they showed us. But x equals 4, therefore 3x plus 7 is not equal to 22. And the reason for that is that law of contradiction. We had the given statement, x equals 4, and then the law of contradiction. The only way that 3x plus 7 equals 22 is x equals 5. But it doesn't. It equals 4. So therefore, 3x plus 7 is, in fact, not equal to 22. So kind of weird, right? You're probably like, this feels uncomfortable. And I get that. Okay, let's look at it in the next one. Prove if x and y are integers such that the product xy is even, then x or y is even. Okay, so this time, step 1, I left it blank. I left step 1 blank. What would you put there? How would we negate this? Okay, so if x and y are integers such that the product of xy is even, then here's my conclusion, x or y is even. So step 1, flipping that around, we're going to assume neither x or y. Well, since we have neither, we should use nor. Assume neither x nor y is even. You could say assume x or y is odd. We could do that as well. We could say assume either x or y is odd. That would work too. Okay, so let's move to step 2. Using that idea and trying to get to a conclusion. Sorry, something flew in front of my face and I was trying to get out. All right, so then it says, so make our conclusion from this, then x and y are both odd. Yeah, so not either or, but neither. Okay, so now we're saying, well, okay, that means that x and y are both odd. This one gets a little hairy. Okay, so we're saying, well, x is equal to 2m, so 2 times some number, plus 1. That makes sure that that is an odd number. And so y is equal times 2 times a number plus 1, some other number. Okay, so it's odd. They're not the same odd number, but they're both odd. And then xy equals the product of 2m plus 1 times the product of 2n plus 1. Okay, so we're going to substitute and simplify. If we do the distribution here, we get 4mn plus 2m plus 2n plus 1, right? We're foiling it. These all have a 2 in them, so we can take, right here, they all have a 2 in them, so we can factor out a 2. So we're left with 2mn plus m plus n, and then plus 1, which is going to give us an odd integer, it says, which is an odd integer because we factored this 2 out. So we're taking 2 times some quantity and then adding 1. That makes it an odd integer. So now we're at that step 3. Okay, that's step 3 that says, hey, we can, since this assumption is false, we're going to wrap this up in my conclusion, conclude this assumption is false, thereby proving that the first statement is true. Okay, so here's that step 3. But xy is even. X times y is even. That's what they said up here. Therefore, x or y must be even. Again, we use at the end, we put our given at the end and the law of contradiction. Those are always going to be like the last 2 things in your step to get us started, is the given and the law of contradiction. Okay, let's look at the next page. I don't know why it's not clearing. There we go. Okay. All right, so first of all, remember, we've got this big remember statement here. Okay, remember that not P or Q is the same thing as not P and not Q. So this is, if we're negating P or Q, we have to get not P and not Q. Now, if we're doing the other one, okay, if we're negating P and Q, then that is not P or not Q. Okay, so if the and is here, then the or is here in the negation. So it's interesting, but you have to remember that. If you're negating an or, you're going to have to use an and. If you're negating an and, you're going to use an or statement in the negation. Okay, so that's good memory to have. Pull back. Okay, so let's look at example 4. Sometimes, well, yeah, we'll do example 4. What's the... Okay, so we want to get that step 1 in here. Okay, so assume the opposite. So let's look at what it's giving us. All right, so given scalene triangle ABC, prove that BD is not a perpendicular bisector of AC. Okay, so let's get to this step 1. I'm just going to write a number 1. Okay, so step 1 is the assume the negation. Okay, so since it says BD is not a perpendicular bisector of AC, we want to assume BD, segment BD, is a perpendicular bisector of segment AC. All right, so now we're ready for the step 2 stuff. Okay, so if BD is the perpendicular bisector, then D would have to be what? Good, a midpoint. So we would say D is the midpoint of segment AC, which also means we can say, and what does that mean about the distance from B to D and C to D? If D is the midpoint. Well, they'd have to be good. They'd have to be congruent. Okay, so we could, or equal. So we could say, and segment AD is congruent to segment CD. All right. All right, well, if we can go from there, what other conclusions can we draw? All right, so if it's a perpendicular bisector, wouldn't these have to be right angles? Okay. So maybe we would say, well, and BD would also have to, so let's say since BDC, angle BDC, and angle BDA are right angles, and so we have those. Ooh, we could say BD is congruent to BD, right? That transitive property. So, and BD, segment BD is congruent to segment BD. Then we could say these are right, like these are congruent because they're, we could say triangle. So that's our sense, right? We have our leg that we can do. We can say triangle ADB is congruent to triangle CDB. And I'm going to write in here, this is that leg congruence because it's a right triangle. Remember, so we just have to prove the two legs are congruent. Okay. I don't know. I proved that they're right triangles. I don't know that we've gotten anything else. This up here, it says it's scalene. But if we have two right triangles back to back, that means, right, if this is a right triangle, or right angle, and this is a right angle, and they're congruent, then these sides would have to be congruent, which would make it isosceles, right? And if we say it's isosceles, but we're told it's scalene, then we've done our job. So let's get to that point. So we would say then, let's see, how do we want to say that they are? So we've got since they're right triangles and the triangles are congruent, then we could say then segment AB would be congruent to segment CB, right? That's that corresponding parts of congruent triangles are congruent idea. then AB would be congruent to CB, and yes, triangle ABC would be, or is, yeah, I should say is, not would be, is isosceles. There's my key, isosceles. We just proved that it was isosceles, which is impossible. So now we can do step 3 and give our given information. But we know, we could say, but it's, this is a paragraph proof more than anything, but it's given that triangle ABC is scalene. Woohoo! Therefore, or so, okay, so segment BD is not, that's what we're going for, a perpendicular bisector of segment AC. Okay. And again, I'm sorry that I wrote this in more of like a paragraph proof. Maybe sometimes that makes that make more sense than the steps out there because it doesn't really have the statements and the reasons. Okay, let me check the time and see about example 5. Okay, I'm going to skip example 5 for now. We might go over it in class tomorrow, but I'm going to skip it for now. It's in your textbook if you want to go back and look at it on page 230. You can follow along there, but I want to flip over to the back and look at a couple of those Venn diagrams and how to use those because they weren't really explained in the notes, but then you have a couple problems from them. Because we want to write an argument from a Venn diagram, and it's actually kind of cool to think about. So I want to make sure we get that in there. So writing an argument from a Venn diagram. So we have modus ponens, which we've talked about. So we have the if P then Q. So that means like if we state P, then we have the therefore Q. Versus the modus tollens. So we still have the if P then Q, but this time we state, well, not Q, therefore not P in our statement. Okay, so let's look at our Venn diagram. So we've got our set. I have our circle here, that's the US. Our circle here, that's VA, so that's Virginia. We have Neil inside the Virginia circle, and, or sorry, Janice inside the Virginia circle, and Neil out here. So Janice is in Virginia. Neil is not in Virginia, and he's not even in the US. Maybe he lives in Australia. Okay? So here's the thing. When we're writing an argument from this, we're saying, if you live in Virginia, then you're a US resident. That makes sense because then you live in the US. That's the same conditional for both of these. If you live in Virginia, then you're a US resident. We have the same conditional for both of these. It's the premise and the conclusion that change. Okay, so for the first one, we're saying Janice, because we want to state a P. So Janice lives in Virginia. That's the P. If you live in Virginia, Janice lives in Virginia. Okay, there's our P. Then you're a US resident. There's our Q. And so we say she is a US resident. We stated our Q. So it's if P then Q, P therefore Q. All right. For modus tollens, it's different. We say Neil is not a US resident. So this is our, here was in the conditional, if you live in Virginia, then you're a US resident. Remember, this was our Q. Well, now we're saying not Q. I actually should have color coded these differently. Let me go back. Try to keep our colors the same so you can see the difference a little easier. Okay, so this is not a US resident. So that was our Q. So this one is not Q. So we state that first. And then we have the therefore. So therefore he is not live in Virginia. So here's the not P from our original one. Okay, so we're changing those around. All right, so let's look at example, and this says 22, I believe, because it's one taken from the book, so we could actually do one together. All right, yeah, so exercise 22 actually instead of example. Exercise 22. So we've got Canada is in North America here, and then Ottawa is that city in Canada. Okay, so let's get our conditionals written. Okay, so we could say for our conditional, Canada is in actually, what does it say? Write the modus ponens or modus tollens argument illustrated by each Venn diagram. Yeah, so we could say Canada is in North America. And I'm just going to put north in. Okay, so Canada is in North America. We could say Ottawa is in Canada. Therefore, Ottawa is in North America. Okay, because we actually only had to do a modus ponens or a modus tollens. We only had to do one or the other, is what I was doing here. So we have, and we could put the if, right? If Canada is in North America. But because the other one has if you live in Virginia, but this one we don't really need the if. Canada is in North America. Ottawa is in Canada. Therefore, Ottawa is in North America. Okay, so you're going to get to do a couple of those in examples 21 and 23 in your homework. Okay, so again, indirect proofs, brand new, kind of brand new concept there. I understand if you're like, this is so weird. The homework is focusing on like writing the conditionals, doing some of the other stuff. 29 and 31 are the only ones where it's like, okay, can you like try this indirect proof? Let's see what you get. Again, look in the back of the book. Check your work. If you are struggling on your indirect proof on those, look in the back. What is step 1? Write it down. Like, let it help you write the contrapositive or the contradiction. Okay, and then go from there. And then work your way through step 2. See what you can figure out on your own. Check it. Use that as like a starting off point. Be like, okay, well, here's what they did first. Let me do that and see if I can figure it out from there. It is okay to struggle. Use your resources to help you get better at the struggle. Okay, I'll see you tomorrow.